Hi, conceptual physics students. I'd like to give you a few hints to help you start the textbook assignment for chapters 2 and 3. Again, these are hints. I'm not going to solve the whole problems for you or even give you hints on all the problems, just a few of the more challenging ones or interesting ones that might be good to get a start. An important note for all the text assignments and worksheets this year: it's not okay simply to write an answer. So if there's an explain problem, you need to do some explanation. If there is an answer that is just a word, tell me how you got it. If there's some mathematics, show your work. As an example, we look at number 22 of chapter 2 assignment. Now, as you look at this one, you have several choices. You're supposed to rank all the choices. So if we have, for instance, on number 22, we have, I believe it is, 4 different circumstances where you're lifting something. And all the ropes are the same and the masses are the same. So for instance, if you want to compare this one, this particular one has 2 ropes. And if you have the 2 ropes, each rope lifts half the force with this one. So if you're comparing this to the one that just has 1 rope, and you say, what will the scale read? Then certainly this one would have a scale reading that would be less. That'll help you, I hope. If you look at number 44, in number 44 you have the hairy heavyweight whose the weight is 1,200 newtons, and we use force vectors to demonstrate which way the force is and how much. 1,200 newtons is being pulled down by gravity. That's the force of gravity pulled down. Now the scales are pushing back up again with the thing that we call the normal force. So there are unknown forces upward. What you can do is either use logic or an equation. If x is one of them and twice x is the other one, these are variables. So in algebra, you could use 2x plus x equals 1,200 and solve that. That's a way to use algebra. Or the numbers are so gentle, you probably could have solved that just using logic. What I'd like to do is switch now to chapter 3. Chapter 3, there are several problems, and I'd like to look, for instance, at number 18 to start us out. And on number 18, we're asking what's the weight of a kilogram brick? So remember, the weight formula is mass times the acceleration of gravity. G is 9.8 meters per second squared. So it's sufficient just to remember that it's 9.8. This is a gravitational constant, so this is an algebra formula that will not be difficult. Show your math work for this. Number 27. Okay. On number 27, we find that Susie has a weight, find the mass. So it's the same idea. It's the same formula, show your math work for this. But this time we're trying to solve for the mass. And so if you take the weight divided by that g, you should be able to find the mass. The mass unit will be in kilogram. Always include the units in problems that you solve. Take a look for a moment at number 37. A reminder, click pause anytime you want to stop and kind of work on these problems while you get some hints. Okay, number 37, there's a junk car crushed into a compact cube. Does its mass change? Now, it's not okay to just write the answer. That's not enough, okay? It says, does the mass change? And it asks a few other questions, but does the mass change? Your answer can't just be no. You should explain why. Something like this could work. Mass is simply counting up the number of atoms, and crushing something doesn't change the number of atoms, so the mass cannot change. That's kind of what I'm looking for in a solution. Take a look at number 48. Number 48 involves a stone being accelerated upward. When the stone is being accelerated upward, that means the upward force has to be greater. So if the upward force is the same, it either won't go anywhere or it'll go a steady velocity. One final question, number 54. The woman has a weight of 500 newtons on Earth. What would she weigh on Jupiter? The important thing about a person's weight and mass. Weight is the force of gravity, and it depends on where you are. But mass does not. So why not find her mass with this formula on Earth? Her mass will be the same on Jupiter. Hopefully that hint will help you a little bit.